So good afternoon, everybody, and welcome to your latest IRIS Early Career webinar. This is your host, Danielle Sumi, speaking from the Incorporated Research Institutions for Seismology headquarters in Washington, D.C. IRIS, which turns 31 next week, is a consortium of universities and an NSF-funded science facility operating programs that enable earth scientists to perform advanced research in geophysics, particularly in seismology. Today's webinar is part of a series highlighting professional development topics to lower the energy and knowledge barriers associated with careers in science, particularly academia. Those interested in additional resources aimed at early career investigators can check out the webpage on the IRIS headquarters website /ECI. Webinars are recorded and archived on the IRIS YouTube channel, and we'll likely send out an email following this webinar with that link. The webinar ground rules are only the presenter, Emily Wolin, and I will speak. If you have a comment or question as the webinar unfolds, then please clearly and concisely type it into the box on the webinar control panel. At the end, I will read your name and question to the speaker. If similar questions have been asked, I may combine them or skip them. If the webinar crashes, which has actually happened once, I will just reboot it and simply click the link you received by email when registering. Also, it helps to know if groups are watching this remotely, so if it's more than just you in a room, please let me know. And also, this webinar is oversubscribed, so if you know that you and somebody else that's in your building are watching this together right now, it would be great if you could share that terminal and work together on that to just open up a few more spots. Today's presenter is Emily Wolin, who is finishing her PhD in the Department of Earth and Planetary Sciences at Northwestern University. Emily's research focuses on North America structure and tomography, primarily with the use of the EarthScope Flexible Array experiment SPREE. In addition, Emily annually presents a lecture on Python and its applications in seismology to early career graduate students as part of the US Array short course, which is why she was asked to present here today. So without further ado, here's Emily to talk about a taste of Python and its capabilities. Thanks, Emily.
All right, well, thank you very much for the introduction, Danielle. Like Danielle was telling you, I'm a grad student finishing up at Northwestern, and I discovered Python, It's probably 2 or 3 years ago now, and I have been presenting at the US Array Data Processing short course. So today I'm going to give you a presentation similar to what I've been presenting there. I think you all got an email saying that you'll have opportunities to sort of follow along in your own terminal window. So I'm hoping that many of you will be following along, and I'll try to give you a few moments to do some of the exercises that I'm showing you here on your own. So the goal for today is just to give you a brief overview of the basics of Python. You're not going to be an expert after an hour learning any programming language, of course, you all know that. But I just want to give you a feel for the language and show you a few examples of how it may help you. Maybe after getting a feel for it, you'll decide whether or not it suits your style and your own applications. Just last plug for the US Array Data Processing short course. I took that as a third-year graduate student, I think, and I've been returning as an instructor. I learned something every time I attend as an instructor. It was very helpful as a graduate student, so I very much recommend that if you are a graduate student or a postdoc that you apply for that course this year. For those of you who may be watching this later on YouTube, you can download a zip file of all of the example scripts and some input files from my website at the address here. I had a few questions before the webinar started about whether you should be using Python 2, of which the latest and last version of Python 2 is 2.7, or if you should be running in Python 3. I think the latest version is 3.4 as of right now. For the examples presented here, the differences are minimal or non-existent. I think the only problems you might encounter if you're using Python 3 is you will have to put some parentheses around your print statements. But that should be it, and I'll point out where you might run into difficulties there. All right, so what exactly is Python, and how is it different from other languages like Fortran or C or MATLAB that you might have encountered in your time in seismology so far? So Python is interpreted. This makes it different from a compiled language like C or Fortran, in which you write code, you have to feed it through a compiler, and then you can run it as an executable. Python, especially if you're running it in an interpreter window, you type commands, it's interpreted on the fly. It's also a relatively high-level language, so you don't have to think a lot about the nitty-gritty of memory management and things like that. There's a lot of things designed to help you in Python, so it makes programming easy, well, easier in something that's a little bit lower level. One of the things that I love most about Python is that it is free and open source, so you never have to pay for a license. That Anaconda distribution that was mentioned in the email, that is a commercial distribution, but they make it free to academics. You can also just go grab the Python source code and build it yourself if you're so inclined. Lots of the most useful modules and libraries for Python are also free and open source, so you never have to pay for a toolbox. It's one of my favorite features about Python, everything being so accessible. I think that jives well with the open data access that we love in seismology. And finally, something that was definitely new to me, having come from a mostly Fortran background, was that Python is object-oriented. And we'll talk a little bit about this with an example that's familiar to all of us who have ever worked with SAC files. But you may have heard that word object orientation thrown around, and that is a feature of Python that we'll get into later. So to start out, I wanted to give you an example of why I use Python. So one question that I have been asking in my research as I'm making new tomographic models is, okay, well, I'm making new models, and that's all well and good. But how good are our current tomographic models of North America, and how can I tell if my model is going to do any better than the current ones? Well, that question is a little bit vague. So to be slightly more specific, I can answer this question any number of ways, but I have chosen to say, well, I know that I can use these current tomographic models, NA07, S40 RTS, pick your favorite one. I can use those models to predict synthetic seismograms throughout North America. So here I have an example of the transportable array stations that recorded the 2011 Mineral Virginia earthquake. There's about 500 stations up there, and for each station I can predict a synthetic seismogram using my tomographic model of choice, and I can compare it to the data that were actually observed. So basically asking, or saying one way of judging the quality of a tomographic model is how well it predicts these regional wave trains. So in order to do that, I need to know the two time series of ground motion, of course, but I also need to be able to keep track of all of the metadata, right? I need to know the station, network, component, and location, so I'm comparing identical components of each station to each other. I need to know the location of the station, and I need to know when the start and end time of my traces are, what rate they're sampled at, because I might need to resample them if my synthetics are calculated at a different sampling rate. I need to know metadata about the event itself, like its hypocenter and origin time, and I also would like to keep track of phase picks, because I might want to, say, cut my waveforms, 20 seconds before the predicted S arrival and, 100 seconds after that or so. So we're all used to SAC, I think. SAC deals with headers really nicely, right? It keeps track of all this information for you. It's got a lot of nice functions. It'll filter for you. It'll demean, detrend, take Fourier transforms. But I personally really don't like writing SAC macros. And if you need to do something that SAC can't do, then you're kind of out of luck. I mean, they have these wonderful SAC input and output libraries, which I've used. But sometimes it would be nice to be able to explore your data, like SAC can do very nicely, very interactively, but also sort of have some more heavy artillery available for you to manipulate your data. So one of the things that I would like to be able to do is to measure the misfit between an observed seismogram, which is here in black in the middle, and a synthetic seismogram, which is here in red. So in order to do that, I use something called a time frequency misfit. And so I input two data arrays, and ideally what I would like to get out is a measure of the phase difference between these two seismograms and the amplitude difference between the two seismograms. So in order, right, and I can also get more information like just the envelope misfit over time or the phase misfit over time, things like that. So this is something that SAC cannot do. But I know that Python can. I'm sort of skipping ahead here and showing you the end result in Python. So how can I get SAC files, these nice data packages that I'm so used to working with, into Python, but also preserving the metadata? So this is where we get into our example of object orientation. So in Python, I can build something called an object, and this object can have attributes like a header that can contain a station name, station latitude and longitude, and also the data itself. So those would be attributes of this object, things that describe it. But I could also define certain functions that can act on or modify these attributes. So I could define a method or a function that will trim my seismogram, given a start time and an end time. I could define a method that filters that trace with various parameters. I could even maybe come up with a function that will remove the response, which would be quite nice. So these are all pseudocode. These are not actual functions built into Python, but something similar already exists in a package called obspy. This is going to be the subject of a future webinar, so I won't touch on that too much today. But even better, I can also use these numerical and scientific libraries to process my data. So I don't have to sit there and write my own seismogram classes and packages. I can use these wonderful ones that already exist in obspy, and I can take advantage of other libraries to process my data. Yes, this is good. Okay, so before we get started, if you are new to programming, I like to set up a text editor with syntax highlighting. That will always make it much easier for you to edit your code. I use Vim, so you can set up your Vim configuration file. Syntax on, this is really, really helpful. This will color the syntax according to the language you're writing in. So it'll help you see if you've missed a parentheses or need to indent something, and line numbers, and turn off visual bells. Not as relevant for this webinar maybe, but just in case you are interested. Okay, so if you did install Anaconda, that came with a package called IPython. That's an interactive Python terminal window. So you can start that, which I'm going to do in my terminal window over here. If you don't have IPython installed, then you can just run a regular Python interpreter, which I will do over here. And you should just be able to get that by typing Python, or it might be Python 2 or Python 2.7, something like that. But I like using this IPython interpreter because it helps you out a little bit with, it lets you access help information more easily. You can explore your objects and methods a little bit more easily, and I'll show you some examples of that in a moment. And then to write your first Python program, it's just as simple. It's print, and this is one of the differences between Python 2 and 3. So in Python 2, I would just say print hello world and hit enter. And there you go. If you are running Python 3, you can try this. You will get an error message saying that you're missing parentheses. And so you can say hello world. And that should work fine. That also worked in Python 2. Just a small difference to be aware of. I believe that's the only difference we should run into today. Please do let me know in the questions and comments if you are running into problems if you're running Python 3. Okay, so Python has, like any programming language, yes?
Oh, somebody just asked if they're supposed to open IPython notebook or IPython Qt console.
Oh, I would say just, okay, so you're running it from Anaconda, the launcher then. What I would do is I would open up a terminal window and just type IPython in there.
Thanks, Em.
No problem. Good question. Thank you. Okay, right. So Python, like any programming language, has a few different variable types. So Python has dynamic typing. So unlike C or Fortran, or Fortran at least I know, you would start your program by saying, I'm defining A as an integer, or A as a string, or a float, or something. Python will change its variable typing depending on how you enter it. So if you type A equals 1, and then I can use this type function to ask, okay, what type of variable are you seeing here? It sees it as a string because I surrounded it in single or double quotes. So double quotes will also do the same thing. All right, so it sees this as a string. I say equals 1 like that. Now it sees it as an integer. Similarly, if I type it in as a floating point number or a complex number, then Python will change the type dynamically. All right. So one of the most useful structures or variable types in Python is a list. So lists are denoted by square brackets with commas in between each element. So we'll define A as a list. And then this is the trip up that always gets me in Python, having come from the Fortran background, is if I type in A of 1, I would originally expect to see this as the first element of my array, but Python is it's built in C, and of course in C arrays start with 0 index, so we have to use A of 0 to get to our first element in the array. So just something to be aware of as you program. This is probably the #1 cause of bugs in my own code. If it's not behaving how it is, I always have to check the array elements. Okay, so one of the nice things about IPython is if you type a dot, and this dot after the variable name indicates that we're going to use an attribute or a method associated with this variable, and then you hit tab, you'll see a list of methods and attributes that can be used on your variable. So if I wanted to reverse my array, you can see over here we have a method to reverse. And if I just hit this, if I type in a.reverse, it tells me that, well, that's the name of the function to reverse the element. So if I want to do that, I have to call it as a function. So this function takes no arguments. So I'm going to leave the parentheses empty. So I've reversed my array, and if I type A, you can see that it has indeed flipped the order of my elements. One thing that you should be wary of with lists in Python, or use to your advantage, I suppose, is that if I say B equals A, and I type B, okay, this is good. We have seemingly made a copy of our array, but if I then reverse the order of A, right, so A is back in its original order. B, if this was some languages, should still be in the reversed order. But in Python, the name of the list refers to the location, or refers to that location in memory. So A and B are pointing to the same place right now. So if I want to actually make a copy of A that will not change when I change A, then I have to do B equals A dot copy. Whoop. Wrong thing, sorry. So, sorry, got my variable types confused. If I say I want B to equal all the elements of A, now I've made a copy of this, and I can reverse A as I like, and B has remained the same. So this can be an advantage if you would like to have two things referring to the same location in memory, but just something to watch out for again. Okay, working with strings in Python is very nice. Lots of nice methods to manipulate strings. So if I just define a string as hello there, I'm going to add some white space after this. And that's my string. Again, if I try to access the first element of the string, I need to remember to use s of 0. And you can take a minute and explore some of these attributes of string. So if I wanted to convert this into capitalize, and if I wanted to capitalize this string, then we've capitalized the first element. If we want to make it all uppercase, we can do that. Very helpfully, if we want to strip off any leading spaces, then we can do that very nicely with this strip method. So lots of nice tools for manipulating strings here. This can be really helpful when you're working with file names and such in your Python scripts. Okay, one of the most distinctive features of Python is the structure of its flow control statements. So these are things like if and for and while statements. So you'll notice that in my code window here, or my presentation, I've indented my the block below my if statement and my for statement. And this is something that in most programming languages you should do in order to produce nice, clean, reasonable code. But Python is different in that you must indent your flow control blocks, or it will not, the interpreter will not interpret that as a code block. So we can say if answer does not equal 42. These always end with a colon, and the IPython interpreter will indent this 4 spaces for you. Some people prefer 8, some people prefer fewer. 4 is in the Python style guide, so that's what I try to stick to. And then in IPython, you'll have to put in another enter after that. And I haven't defined answer yet, so I'm going to say answer is 17. Run this again, and I don't have the correct answer. So that is one of the that's one of the most distinctive features of Python is its mandatory indentation. And I think this makes Python code very nice to read because you have to indent things or it won't run at all. So that helps keeping your code clean. So we'll do a for statement here. And I've used a built-in Python function here, the range function. So this is going to generate a list of 0 through 4, so 5 elements. So the length of this is 5. Nope. There we go. So I have 5 elements in my list, and then my for statement, I will say for each element in this list, print hello world 5 times. So there you go. And again, we've spaced this in 4 spaces.
Emily, there's a couple questions that have been coming in about like the libraries that some people are getting syntax errors when they do like a dot or s dot.
Okay.
Could you comment on that?
Let's see here. So you're getting syntax errors when you do something like this?
Or s dot, yeah.
Okay. So let's see here. So if you type in one of these things like a dot sort or something, what sort of error messages are they talking about?
Somebody's getting, they just, when they type in like a dot, it just says like syntax error, invalid syntax. I think it may be highlighting on the dot. Is that?
Okay, right. So if you just type in a and hit enter, that's probably what you're seeing. So if you're in the IPython interpreter, I'm hitting a dot and then the tab key, and that should pull up this this list of methods. If you are just in the regular Python interpreter, I'll switch over here, then nothing will pop up. If I hit tab, it just keeps tabbing. So then you would have to go to the documentation or something like that in order to figure out what methods are available with that variable type or class.
Okay, great. Thanks, Emily.
No problem. Yeah, if you're in IPython and you hit tab after pretty much anything, it will give you some useful information. You can also use a question mark, and it'll tell you about its type and what it looks like and its length and all these useful things. So if you're in the IPython interpreter, that's a great way to learn more about your what you're working with.
Great.
So moving on, sorry, what was that?
I was just going to say thanks.
Oh, no problem. Glad. Thank you for bringing up the questions. Should have been more clear about that. Okay, so like I mentioned earlier, one of the advantages of Python is that you can load modules. So these are you can, if you've used MATLAB before, you can think of these like the toolboxes in MATLAB. But Python doesn't know it has any modules unless you specifically ask for them. So I would like to use the OS module here. That's the operating system module. So I'm going to say import OS. Import is the command you use to say I would like to import this package and make its contents available. So now I've imported that package, and I can say help OS, and this will give you a little bit of information about this module, where you can find documentation, a description, things like that. And we can scroll down and see lots of information here. Okay. Let me check and make sure that this works in. Okay. Right, and this works in your regular Python interpreter as well. So you don't need to be in IPython to use this help command. Okay. I am going to explore this OS module a bit, so I'm going to type OS dot and then hit tab again in IPython. You can see that there are a lot of things associated with this operating system thing. So as seismologists, we maybe are not going to use a lot of these, but one thing that we do a lot is set environment variables like the path. You might want to know what your home directory is, so I can say I want to see a list of all the environment variables, and oh boy, we've got a lot. You can see I've got my path set up here, so that's available to you inside of Python. Got a bunch of helper functions defined here with GMT. My home directory is defined somewhere up here, and so is my username. So if I wanted to say, and this os.environ attribute is a slightly different kind of variable than the lists that we were talking about before. This is something called a dictionary. So if you look at the structure here, you can see that if I go up to here, path is a keyword that is then matched with a value, which is a string containing my path. So to work with these in Python, what we do is you can access that variable using a keyword instead of its position in the array. So instead of having to count through and say, oh, I want the 34th element of this array, I would like the entry in the environment attribute that matches user, and we can see that that's Emily. So my username on this computer is Emily, and we can access that using this environment variable. So that is how to import a module, and then a little bit about dictionaries. So if you downloaded the examples beforehand, you'll have a file called mymodule.py, and its contents are shown here. So I'll pull that up in Vim. So I've, like we just did, I'm telling Python that it's going to need to import the OS module, and I've defined two functions here. So I defined one that's very simple, just to say hello. This function has no arguments, and you'll notice that functions, just like flow control statements, are always indented for spaces. So we have, like we just did, my name is defined as this entry in the dictionary, and then I'm using a print statement to say hello, and this is a formatted print statement. So this is saying format this variable and put it in this location. I've defined a second function in this module. So a module can be a collection of functions, saying that just adds two numbers. This is a very rudimentary function. You normally wouldn't want to do something this elementary, but just as an example. And this function has arguments. So we have A and B. So when I call this module, I'm going to give it two arguments. It's going to print a string with A, B, and C inserted in their appropriate place, first, second, and third place. And then it's going to return a value. So if we were going to run this or use this module, I would say import my module. Whoop. Where am I working? Okay. It would help if I was in the correct directory. Okay, and now we can see that I do have the modules in this directory. So I can say import my module. When you learn a little bit more about Python, there's an environment variable called the Python path you can set, and you can, just like your regular path in a shell, this will point you to the location of various modules, so you don't have to be in the same directory to run them. So I've imported my module, and then to use the functions in this module, you need to say I'm using my module, and then I want to use the say hello function. And that didn't take any arguments. So we can see that calling this function just says hello, and then you should see your username here, whatever that may be. If I wanted to use that second function, right, so this was the say hello function, no arguments. If we wanted to use add these, then we see that this returns a variable. So we can say A equals my module, add these. And the nice thing about IPython, again, is if you start typing the name of module and hit tab, it'll complete it for you. So that saves some typing. So again, we see we got our print statement back. So we have our input values printed here, and our output value, we can see, has been stored in the variable that we assigned to it. So this is how you would define functions in a Python script if you were so inclined. Right, so this is the example we just showed. A nice thing about Python is if you have a module with a very lengthy name and your fingers are getting tired, you don't want to type that much, you want to keep your code a little bit cleaner, you can say import my module, but then you can also tell Python how you would like to refer to that. So I could say I don't want to type my module every single time I call one of these functions. I can say as mm, and then whenever I type it knows which module I'm talking about. So exact same result there. There are certain libraries that have standard, or sort of standard, importation names. Like you'll see NumPy, which is a mathematical library, often imported as NP. There's a visualization library called Matplotlib that is often imported as MPL. Sometimes parts of it are imported as PLT, things like that. So just things to be aware of as you start looking into example code and example scripts, things like that. Okay, so one thing you can do, in addition to writing your own functions, is you can define a class. So a class is an object that has its own attributes, and you can define methods to modify the attributes of that object. So once again, in the examples, I've defined a class called swallow. So I'm going to describe different types of birds here. And I would like to describe certain of their attributes. So I have a species attribute here. I'm going to say whether this bird is carrying a load or not, so it's load status. And then this initiates the class. So when I say, when I first define my bird here, I'm going to say from bird classes, import swallow. So now I have this available to me, and I can say bird is an object of the swallow type. And looking at this, we can see that it has 3 attributes, right? So I have a species, I have a load status, and then I have a velocity, so how fast that bird is moving. I realize this is not seismologically based, but Python was named for the Monty Python television show, so I feel this is appropriate. Okay, so when I initiate this class, I'm going to give it a species. So I'm going to say this is African swallow. And I'm going to say its load status is unladen, which unfortunately wraps around a bit in this interpreter. But you can see this here in the PowerPoint. So I can then inquire what the status of the bird is. Is it laden or not? So we can see it is unladen, just as I specified when I initialized this object. And I can ask what the bird's velocity is. You can see that it's 11.0 meters per second, or whatever you like it to be. So this is defining the attributes of my swallow. I've also defined a few methods that can act on this class. So I have a method called giveCoconut. So if it's not carrying a coconut, then I will change its status and I will reduce its velocity. So I can say, and if I now ask about its load status, it will tell me that it is laden with a coconut. And if I ask about its velocity, we can see that that has been reduced. So with this class, we can now answer important questions such as, what is the airspeed velocity of an unladen swallow? Which might save you getting tossed off a bridge or two if you are on a quest. Okay, so you can write a class for anything you like. I have played around writing classes to describe different events, different origins and moment tensors and such. There are plenty of these defined in OBSPy for nice seismological examples. So if you are interested in learning about those, then I highly suggest you tune into the next webinar. Well, it may not be immediately following webinar, but I know that they're planning to host one on OBSPy, and you can learn all about the wonderful classes that have been written to help you out with seismology examples. Okay, a little word on some useful modules. NumPy, I mentioned earlier. This is the package you want to use if you're doing any scientific computing with Python. Mostly I use this because it gives you access to arrays and linear algebra capability. So this is extraordinarily useful. Any scientific computing you do, you'll probably end up running into NumPy. I've also heard this pronounced as NumPy, but for consistency with the name of the language Python, I pronounce it NumPy. Matplotlib is a plotting library which you can use to make absolutely any kind of graph you would ever imagine. I highly suggest you go and check out the gallery. I am sort of still tied to GMT for my mapping, but almost everything else I like doing in Matplotlib. One of the really nice things about using Matplotlib is that from a terminal window, it'll give you an interactive plot. So if you've ever made a GMT plot and just wished you could zoom in without changing your axes limits in your script, and zoom in and out and resize it and such, Matplotlib is for you. Just absolutely fantastic. Bit of a steep learning curve, but once you get started, it's amazing, and the gallery has lots of great examples to help you out. So definitely check this out. It has a part of it called PyLab that if you are used to plotting in MATLAB, using function calls to change your x-axis labels and y-axis labels and such, it'll feel very familiar to you. Finally, SciPy is a collection of different toolboxes and algorithms. It contains NumPy and Matplotlib within it. It's got tons of signal processing toolboxes. It's got some great filters, all this kind of stuff. So I highly suggest that if you don't have that installed, definitely check that out as well. And finally, the wonderful OBSPy, which makes life so much easier when you're processing seismological data in Python. Definitely check this out. Follow the upcoming webinar. Get on the mailing list. It's definitely a helpful tool. Okay, So in the first part of this webinar, we covered sort of the basics of Python. We talked about data types, a little bit about what object orientation is, the fact that an object can have attributes and methods that can modify it. We learned about how Python does flow control statements and that you must indent your code. And you learned how to import modules and write your own simple functions. So I guess before I move on, have there been any questions, Danielle? Okay, I think we are good. So moving on, I wanted to show you an example of a very simple thing that we do all the time, which is just fitting a line of values. So one of the sample codes you got, which is my line fit, will generate a linearly spaced array of x values, calculate a function at each of those points. We'll plot that line, and then it adds random noise to your data, fits a line through those noisy data, and then plots the best fit line to those. So if you want to run this from within IPython, you can just say run myLineFit.python, and that'll take a minute and show up. So we have data, which are the green circles here, and then we have an original line, which is shown here in blue. I added noise to the points to get the green circles, and then fit a line to them, and that's the best fit line is now the red line. So let's take a look at the content of that module. So if you're running this in terminal, you'll have to make it executable. And then if we look at the first line of my line fit, you'll see that it uses this sort of funny user bin env Python. And this is there to make sure that whichever Python interpreter you're using is the first one in your path. So you could set this to a specific system Python. So I have the Anaconda module installed right now. So I'm running this out of my home directory /anaconda/bin. So I could put that up here if I want to use that specific version of Python. But if I'm just saying I want whichever one I would normally use by running from a shell, this is what I use. So Python, unfortunately, can be a little bit tricky with, are you using a system Python? Are you using a different distribution? This line up here in the top of a script, make sure that you're using whichever Python is the first one that you'll find on your path. Okay, so enough about that. I'm importing a couple of useful modules. So you'll see here I'm importing NumPy as NP. I'm importing the pyplot part of the matplotlib module as PLT. And then I'm importing the stats module from SciPy, which you'll also occasionally hear pronounced Skippy, which always makes me laugh. Okay, so we are generating some linearly spaced x values, and I know I'm going through this a little fast, but you can download the examples and go through them on your own time. We're using the NumPy module to generate a linearly spaced array between xmin and xmax with a certain number of points. We define a line, and then we plot this. So this is what plots our blue line here originally. And this is a little bit like MATLAB in that you can call the plot and then decide when to show it. So I've plotted this. Now I need to add some random noise, plot my noisy data points, and I'm going to use two things to fit this line. So the first one I used was just the linear regression package from stats, which if you remember is part of SciPy. And in my terminal window, I had some output saying what the slope and intercept from SciPy are. If you really enjoy looking at ugly code, you could do this yourself and solve the generalized inverse problem, your GM equals D, and solve the inverse problem of that. And you could use NumPy to do that. Do some linear algebra here. This is a horrible bit of code you can unravel if you really would like to later. But that will also give you a slope and an intercept. And that is what we've plotted on here in the red line. I would tell it to give us a location, and then show the plot so that you can see the results of that here. So that little script, we've generated our data, we fit a line to it 2 different ways, and then we can show the results of plotting. So there you go, nice simple example of fitting a line. I, in the future, would always use this stats.linregress package, but now you've seen a bit of linear algebra from NumPy as well. So there you go. You should have a plot that looks something like that popping up on your screen. Just a little bit of a glimpse into ObsPy and what it can do for you. If you have a waveform and you want to look at it, if I was working in SAC, I would just open up SAC, type in read my SAC file, and plot it. It's exactly that easy in ObsPy as well. So I'm just going to say from ObsPy, import read, and that'll take a minute. There we go. And then I'm going to say that this stream object is read. This is the seismogram that I put in that example package. So if you have the examples, you should be able to read this. And then this stream object has different methods associated with it. And you can see we have methods to decimate and detrend and filter and rotate and things like that. So lots of wonderful things here in ObsPy. I just want to look at the waveform. So I'm going to say plot. And there it is. So this is a waveform from the Mineral Virginia earthquake recorded at one of the TA backbone stations in Minnesota. So nice little recording here in my window. I can zoom in. I can zoom out. Really nice for just taking a quick look at your data. I can do things like filter it. So I can say, I'm going to do a low pass. And now I have my filtered waveform here, filtered below about 16 seconds. So nice, quick and easy way of filtering your data there. Lots of other things that you can try out in ObsPy later if you want. I think that the ObsPy GitHub page has instructions on how to install that if you are interested. Okay, so yeah, there's our nice little waveform there. Another quick feature of ObsPy makes it really easy to plot focal mechanisms. So it's got this beach ball class and methods. You can say from obspy.imaging.beachball. I want to import the beach ball here. And now we've got that. And so I'm going to define a moment tensor with a strike, dip, and rake. And then use this beach ball class to plot a beach ball. And there you go. So it's that easy. You can either give it a strike, dip, and a rake, or you can give it your 6 moment tensor elements in the conventional order, like I've done in this second line here. So if you need to plot a moment tensor really fast, here's a nice little tool for you. So there you go. And it can also handle non-double couple events, which is nice. Okay, as a final example, again, part of the example package that you can download from the website, I've given you a little Python script that will plot anything as long as it's in a 2-column ASCII file. So again, we are importing NumPy here. We use the PyLab module from matplotlib to import some things that we'll use to change figure attributes. We define a function to plot the data files, and we define the main part of our program. So we read in the names of our data files. We have a usage message, which is helpful if you call it without any arguments, so to tell you what it's meant to do. We call our plot data function for each data file, give it a legend and a title, and then finally tell PyLab to show this. So I'm going to say run plot anything.py, and in that same example package, you had a few files, just plain ASCII files that start with VS. So I'm going to plot those. We've got our nice interactive window open here. Again, we can move this around and shift it. And I have left the labels off here so that you can edit them as you like, but you can see we've got a plot of depth and S-wave velocity here. So we've got two commonly used velocity models, AK-135 and SNA. And you can plot those. You are interested in only the lithosphere, you can zoom in on that. Very nice way to explore your data like that. Okay, so if you want to run it in terminal, again, change the mode, run it. And again, you'll notice this shebang up here telling me to use whatever I find first in my Python path. Okay, we are getting close to the end here, but if you want to learn more, there's a really nice IPython notebook on the OBSPy tutorial page. You can open it up here, download it, and then run it from your IPython notebook. And that has lots of nice examples of, goes into a little bit more detail of some of the things I've shown here, and also some new things and a little bit of OBSPy in there as well. So if you want to learn more about Python, I highly recommend starting with this, A Byte of Python. This is a PDF file available online. He has a tutorial for Python 2.7 and 3.4. They're very similar, like I said. If you're just starting out learning, I recommend 3.4 because that's the branch of the language that's actively being developed. This is a great, great tutorial. This is how I learned Python. If you're just starting programming, it's good. If you already have some programming background, it's good. So definitely give that a look. Like I said, there's tutorials on the OBSPy page. And then there are two resources down here that are a little bit more computationally and science focused. This Python Scripting for Computational Science is a book, and then the Python Scientific Lecture Notes are available on from SciPy on that same website. So both of those also definitely worth taking a look at. Small plug for a Python package developed here at Northwestern. This is AIMBAT. This is a Python package for teleseismic travel time picking. And this is still in development and is in Python 2.7, but we are constantly working on updating it. And if you want to pick your teleseismic travel times in a GUI in a really nice sort of user-friendly format, definitely give this a look. Website's down at the bottom. And with that, I think that's it. And thank you very much for your time.
Thank you, Emily. I think that was really a good introduction to Python. We do have a few questions.
Oh, excellent.
Shreya Kanakia, sorry, I'm sure I butchered that. Does the OBSPy, SciPy, or plotting module of Python come inbuilt with the Anaconda version, or do they all have to be downloaded separately?
So OBSPy will be separate. I believe Anaconda should come with NumPy and SciPy and Matplotlib.
Great. And then somebody would like to know if they can get a copy of your PDF presentation. So would that also be included maybe on your downloads on the website?
Absolutely, yes. It's not in that that tar file, but I will put it up somewhere on my homepage. So if we send out an email after the webinar, I'll let you know where you can download those.
Great. And then everyone else is just writing in saying how great it was. So,
awesome.
Yeah, like 4 or 5 different people just wanted to say that they thought it was really great and excellent.
Oh, good. Yeah, I'm glad you all enjoyed it. I know it was a bit of a kind of a fire hose, a lot of information at once, but I hope I've at least piqued your interest and encouraged you to go check it out a little bit more for yourself.
And as Emily mentioned, the webinar has been recorded today and will be posted on the YouTube channel, as well as the OBSPy webinar is upcoming and should be taking place at the end of May. So watch out for that.
All right. Yeah, I'll be listening in on that one too.
Great. Well, thank you very much, Emily.
All right. Thank you, everyone.
Okay. So that concludes this webinar, and stay tuned for the next one, which should be by Doug Weens. So thanks.
Ooh.